Gazing into the night sky, it's easy to think what we're observing is the universe itself. But in truth, every star visible to the naked eye is part of just one system, our own Milky Way. Beyond it lies an almost unimaginable expanse filled with countless other galaxies, drifting silently through the depths of space. A galaxy isn't just a cluster of stars, it's a vast ecosystem containing gas, dust, dark matter, and sometimes a supermassive black hole at its heart. Stars are born in its nebulae, live out their lives, and return their material to the galaxy when they die, creating new generations of stars. In this way, galaxies evolve. They are living systems on cosmic timescales. The variety is staggering. Some galaxies stretch over hundreds of thousands of light years. Others are so small they barely hold a few million stars. Some spin in elegant spirals. Others exist as featureless ellipses or chaotic clouds of light. And yet, no matter their form, all galaxies share the same purpose. They are the basic units of the universe's structure. Without galaxies, the cosmos would be an empty sea of gas and radiation. It's within them that matter condenses, stars ignite, and planets form. Every element heavier than hydrogen, including those in our own bodies, was forged in stars within galaxies. To understand galaxies, then, is to understand the story of everything, from the first light after the Big Bang to the worlds capable of observing it today. Today, we'll explore the many faces of these cosmic giants, how they form, why they differ, and what they reveal about the evolution of the universe itself. Spiral galaxies are among the most visually stunning structures in the universe, with their flat, rotating disks of stars, gas, and dust. They often feature winding arms that spiral outward from a dense central bulge. These arms are not just aesthetic, they are sites of intense star formation, where gas clouds collapse under gravity to ignite new stars. A typical spiral galaxy can contain anywhere from tens of billions to over 100 billion stars. The Milky Way, our own galaxy, is also considered a spiral galaxy with an estimated 100 to 400 billion stars. Its spiral arms stretch over 100,000 light years across, curving gracefully as they orbit the galactic center. Spiral galaxies are classified based on how tightly their arms are wound and the size of their central bulge. The Hubble sequence divides them into SA, SB, and SC types. SA galaxies have tightly wound arms and a large bulge, while SC galaxies display more open arms and a smaller bulge. This structure influences the dynamics of star formation, with loosely wound spirals often hosting more active stellar nurseries. Several iconic spiral galaxies can be observed with telescopes. The Andromeda Galaxy, located about 2.5 million light-years from Earth, is the nearest spiral galaxy to the Milky Way and will eventually merge with it in roughly 4.5 billion years. The Whirlpool Galaxy, or M51, located 23 million light-years away, is famous for its clearly defined spiral arms and interaction with a smaller companion galaxy. Another striking example is the Pinwheel Galaxy, M101, with its broad, loosely wound arms spanning 170,000 light-years. At the heart of many spiral galaxies lies a supermassive black hole, influencing the motion of stars near the core. Spiral arms themselves are not static structures. They are density waves, regions where stars and gas move together like a traffic jam, triggering bursts of star formation as clouds are compressed. Spiral galaxies dominate the local universe, making up roughly 60% of the galaxies in our cosmic neighborhood. They are dynamic, evolving systems, balancing the calm rotation of their disks with the chaotic births and deaths of billions of stars. Observing them allows astronomers to study how matter organizes itself on grand scales, providing insight into the life cycles of stars and the gravitational choreography that shapes the universe. In essence, spiral galaxies are cosmic masterpieces, elegant, dynamic, and alive with the constant rhythm of creation and evolution. Barred spiral galaxies are a fascinating subset of spiral galaxies, distinguished by a central bar of stars that stretches across the galactic core. This stellar bar is more than a structural feature. It acts as a cosmic highway, channeling gas and dust from the outer regions inward toward the nucleus. This inward flow fuels bursts of star formation near the center and can even feed the supermassive black hole that resides there. Observations indicate that roughly 2/3 of all spiral galaxies contain some form of bar, suggesting that bars are a common and perhaps inevitable stage in galactic evolution. The bar itself is a dynamic structure, formed through gravitational instabilities within the galactic disk. Stars within the bar orbit in elongated paths, creating a gravitational torque that redistributes angular momentum and drives the inward migration of gas. Barred spiral galaxies are classified in the Hubble sequence as SBA, SBB, and SBC, reflecting the size of the central bulge and the openness of the spiral arms. SBA galaxies feature tightly wound arms and a large central bulge, while SBC galaxies display more loosely wound arms and a smaller bulge. SBB galaxies are the intermediate type, featuring a medium-sized bulge and moderately wound spiral arms. This variation influences the rate of star formation and the overall evolution of the galaxy. Several well-known barred spirals are visible from Earth. The Milky Way itself is now recognized as a barred spiral, with its central bar stretching roughly 27,000 light-years across. NGC 1300, located about 61 million light-years away in the constellation Eridanus, is a textbook example of a grand design barred spiral, with a sharply defined bar and sweeping spiral arms. The Southern Pinwheel Galaxy, or NGC 1365, approximately 56 million light-years distant, is another striking barred spiral, featuring a massive bar that drives a vibrant ring of star formation around its nucleus. Bars play a crucial role in shaping the long-term evolution of spiral galaxies. By funneling gas inward, they not only trigger central star formation, but also influence the growth of the central black hole. Over billions of years, this process can transform the galaxy's appearance, gradually altering the balance between the disk, the bar, and the spiral arms. In essence, barred spiral galaxies reveal the interplay between structure and dynamics on a grand scale. Their elegant bars guide the flow of matter, orchestrating the birth of stars and the evolution of their disks. Observing them offers insight into the mechanisms that govern galactic life, showing how cosmic architecture can direct the very processes that light up the universe. Elliptical galaxies are the universe's ancient titans, massive spheroidal collections of stars that lack the spiral arms and structure of their disc-shaped cousins. They appear smooth and featureless, dominated by old red stars, and contain little gas or dust. Because of this, star formation in elliptical galaxies is minimal, and most of their stars are several billion years old. These galaxies vary widely in size. The smallest, known as dwarf ellipticals, can contain just a few million stars, while the largest, called giant ellipticals, can host over 100 trillion stars and stretch more than 1 million light-years across. Giant ellipticals are often found at the centers of galaxy clusters, where they dominate the gravitational landscape. Elliptical galaxies are thought to form primarily through mergers. When two or more galaxies collide and merge, their stars are redistributed into a roughly spherical shape, while much of the interstellar gas is consumed in a final burst of star formation or expelled entirely. This process leaves behind a massive, slowly rotating galaxy composed almost entirely of older stars. Some of the most studied elliptical galaxies provide insight into their scale and structure. M87, located in the Virgo cluster about 53 million light-years away, is a giant elliptical notable for its supermassive black hole, famously imaged by the Event Horizon Telescope. Another example is M49, also in the Virgo cluster. which contains roughly 1 trillion stars and serves as a gravitational anchor for smaller companion galaxies. NGC 1132, about 318 million light-years away, is an isolated elliptical galaxy that exemplifies the relics of ancient galactic mergers. Elliptical galaxies often host globular clusters, densely packed groups of stars that orbit the galaxy as a whole. The largest ellipticals can have tens of thousands of these clusters, each a relic of the galaxy's violent past. In the cosmic landscape, elliptical galaxies represent the end point of galactic evolution. They are quiet, stable, and ancient, contrasting sharply with the dynamic spiral and barred spiral galaxies. By studying them, astronomers can trace the history of galaxy formation and understand the processes that shape the large-scale structure of the cosmos. Lenticular galaxies occupy a quiet middle ground between the active spirals and the ancient ellipticals. They share the flat, disc-like structure of spiral galaxies, but lack the bright, well-defined arms that make spirals so distinct. At the same time, they resemble ellipticals in their older, redder stellar populations and low levels of star formation. In many ways, they are the transitional phase of galactic evolution, a bridge between youth and age, structure and stillness. Designated as Type S0 in the Hubble sequence, lenticular galaxies often contain large bulges surrounded by smooth disks. Unlike spirals, their disks hold little gas or dust, which means new stars are rarely born. Most of their stars are several billion years old, and the bluish hues of young stellar nurseries have long faded into the yellow and red tones of mature stars. Astronomers believe many lenticular galaxies were once spirals that lost their interstellar material. This can happen in dense environments such as galaxy clusters, where interactions with surrounding galaxies or hot intracluster gas strip away the cold gas needed to form new stars. Over time, the spiral arms fade, leaving behind a bare stellar disk, a galaxy frozen in transition. One of the most striking examples is NGC 5866, located about 44 million light-years away in the constellation Draco. Sometimes called the Spindle Galaxy, it's seen edge-on from Earth, revealing a thin, dark dust lane cutting across its bright central bulge. Another well-known lenticular is NGC 2787, about 24 million light-years away, featuring a prominent central bulge and faint, smooth disk. And in the Virgo cluster lies NGC 4762, a remarkable edge-on S0 galaxy whose thin, lens-like shape perfectly illustrates the term lenticular. Though often overlooked, lenticular galaxies play a crucial role in understanding how galaxies evolve. They demonstrate how interactions, gas depletion, and environmental effects can reshape once active systems into quiet, aging structures. Observing them helps astronomers piece together how spirals fade and how galaxy clusters influence the life cycles of their members. Lenticular galaxies may lack the brilliance of star-forming spirals or the sheer mass of giant ellipticals, but their subtlety carries its own significance. They stand as reminders that even in the cosmos, change is inevitable, and that beauty often lies in the quiet moments between transformation and rest. Not all galaxies conform to graceful spirals or smooth ellipses. Some defy symmetry altogether, chaotic, scattered, and unpredictable. These are the irregular galaxies, systems that refuse to follow the neat order of the Hubble sequence. Their shapes are distorted, their stars scattered unevenly, and their structure often torn apart by gravitational encounters. Irregular galaxies are typically rich in gas and dust, which fuels vigorous star formation. Many are small compared to spirals or ellipticals, containing only a few billion stars, yet they burn brightly with clusters of young, blue stars and glowing nebulae. Their disordered appearance is often the result of past interactions, close encounters or collisions with larger galaxies that disrupted their structure. Astronomers classify them into two main groups, Type 1 and Type 2 irregulars. Type 1 irregulars still show hints of structure, perhaps a weak disk or central concentration. while type 2 irregulars are more chaotic, lacking any discernible pattern. Despite their disorder, these galaxies offer valuable clues about how galaxies form and evolve, especially in the early universe, where collisions were far more common. A classic example is the Large Magellanic Cloud, located just 163,000 light-years away. It's a companion to the Milky Way and home to the Tarantula Nebula, one of the most active star-forming regions in our galactic neighborhood. Its smaller neighbor, the Small Magellanic Cloud, lies about 200,000 light-years away and also shows signs of tidal distortion caused by our galaxy's gravity. Both are prime examples of dwarf irregular galaxies shaped by their interactions with the Milky Way. Another well-known irregular is NGC 1427A, about 52 million light-years away in the Fornax cluster. It's plunging through the cluster at high speed, triggering a wave of star formation as gas clouds collapse under the pressure. The result is a galaxy in turmoil, asymmetric, turbulent, and brimming with new stars. Irregular galaxies make up a smaller fraction of the nearby universe, roughly 20% of known galaxies, but in the early cosmos, they were far more common. The young universe was a chaotic place where galaxies frequently collided and merged, constantly reshaping themselves. Many of today's spirals and ellipticals likely began as irregular systems that slowly settled into order over billions of years. In their disarray, irregular galaxies capture the universe's restless energy. They show us that cosmic beauty doesn't always come from symmetry or balance. Sometimes it emerges from chaos itself. Dwarf galaxies may be small, but they are among the most numerous and influential structures in the universe. Containing anywhere from a few million to a few billion stars, they are dwarfed by giants like the Milky Way, yet they play a fundamental role in shaping galactic evolution. These faint, compact systems are often described as the building blocks of larger galaxies, remnants of the early universe that helped assemble the vast cosmic structures we see today. Most dwarf galaxies are irregular, elliptical, or spheroidal in shape. They tend to have low surface brightness, making them difficult to detect even when they lie relatively close to us. Despite their modest size, they can contain surprisingly complex histories shaped by gravity, star formation, and interaction with larger neighbors. The Large Magellanic Cloud and Small Magellanic Cloud companions of the Milky Way are two of the most famous examples. Both are classified as dwarf irregular galaxies. The Large Magellanic Cloud spans about 14,000 light-years and contains tens of billions of stars, including the massive star-forming region known as the Tarantula Nebula. The Small Magellanic Cloud, at roughly 7,000 light-years across, contains about 3 billion stars and shows clear signs of tidal distortion caused by our galaxy's gravity. Both are active laboratories for studying how dwarf galaxies evolve under external forces. Another example is the Sculptor Dwarf Galaxy, located about 290,000 light-years away. It's a dwarf spheroidal galaxy, faint, old, and nearly devoid of gas, populated mostly by ancient stars. Similarly, the Fornax Dwarf Galaxy, around 460,000 light-years distant, contains several globular clusters and provides a glimpse into how small galaxies enrich their environments with heavy elements over billions of years. Astronomers estimate that the Milky Way alone may be surrounded by more than 50 dwarf galaxies, many of them faint and only recently discovered. These satellites orbit their host galaxies, sometimes merging with them over time. When this happens, their stars are absorbed, contributing to the growth of the larger galaxy's halo. In fact, much of the Milky Way's outer regions are thought to be built from the remnants of long-consumed dwarf galaxies. Though often overlooked, dwarf galaxies are crucial to our understanding of cosmic structure. They trace the distribution of dark matter, act as sites of chemical enrichment, and reveal the earlier stages of galaxy formation. Their simplicity makes them powerful tools for studying processes that are harder to untangle in massive galaxies. In the grand scale of the universe, dwarf galaxies may seem insignificant, yet without them, galaxies like the Milky Way might never have formed. Not every galaxy fits neatly into the standard categories. Some are twisted, stretched, or reshaped by forces far stronger than their own gravity. These are the peculiar ring and interacting galaxies, systems that show what happens when the universe pushes against its own rules. Peculiar galaxies are those whose shapes have been heavily distorted, often by tidal interactions or past collisions. Their structures can be asymmetrical, lopsided, or warped, making them difficult to classify within the normal Hubble sequence. One example is NGC 1316, also known as Fornax A, located about 62 million light-years away. It shows shells, ripples, and dust lanes that hint at a history of multiple mergers. Another well-studied case is Centaurus A, roughly 13 million light-years distant, a peculiar galaxy with a prominent dark dust band cutting through an elliptical core, the result of a merger between a spiral and an elliptical galaxy. Among the rarest forms are ring galaxies. These systems feature a bright circular ring of stars and gas surrounding a relatively empty center. The ring often forms when a smaller galaxy plunges directly through the disk of a larger one, sending out density waves that trigger a burst of star formation. The most famous example is Hoag's object, located around 600 million light-years away. It consists of a nearly perfect outer ring of hot blue stars surrounding a golden older core. Another striking ring galaxy is Cartwheel Galaxy, about 500 million light-years away in the constellation Sculptor. Its dramatic ring was likely formed after a direct collision with a smaller galaxy roughly 200 million years ago. Then there are interacting galaxies, where the gravitational pull between two or more galaxies creates bridges, tails, and spirals that stretch tens of thousands of light-years into space. Interactions can compress gas clouds, trigger intense star formation, or completely reshape the galaxies involved. A well-documented pair is the Antennae Galaxies, located about 45 million light-years away. Their long tidal tails resemble insect antennae, formed as the two galaxies undergo a major merger that will eventually leave behind a single larger system. These unusual galaxies offer clues about the dynamic nature of the universe. They show how gravity sculpts matter on the larger scales, how collisions can ignite new generations of stars, and how even seemingly stable galaxies can be transformed over time. Many of the orderly spirals and ellipticals we see today carry subtle traces of these violent events. Warped disks, faint tidal streams, or rings left from past encounters. Thus, these unusual galaxies are the smoking guns of cosmic evolution, showing the raw power required to build the colossal structures of the universe.